Today I'm gonna be talking about another approach for contrastive learning, another way that we can use contrastive learning, which is called F-mutual information. This paper in 2021, and this is a positive sample. Self-supervised contrastive learning is an emerging field due to its power in providing good data representation. Such learning paradigm widely adopts the info and CE loss, which is closely connected with maximizing the mutual information. In this work, we propose the F-mutual information contrastive learning framework, which directly maximizes the F-divergence-based generalization of mutual information. We theoretically prove that with mild assumptions, our FMICL naturally attains the alignment for positive pairs and the uniformity for data representations. These are the two main factors for success of contrastive learning. This is the network architecture of MF mutual information CL. So we have augmentation as usual. We have two augmentations, and here we create positive pairs. And using the Gaussian kernel and average over that, we have two loss and alignment and uniformity. But if we thumb them, and then we work in the framework of mutual information. Infomax can be seen as a lower bound of mutual information between the views. And info and CE can be interpreted as a lower bound of the mutual information between the two views of data samples. This explanation is consistent with the Infomax principle. Nevertheless, it has been shown that maximizing a tighter bound on the mutual information can result in worse representations, and reducing the mutual information between views while only keeping task-relevant information can improve the downstream performance. And these observations suggest that maximizing the mutual information may be insufficient in contrastive learning, and thus a better objective design is required. There are three contributions in this interesting paper. First, they propose a novel framework for contrastive learning, which is called FMICL, by encouraging the contrastiveness of positive and negative. So BYOL, Simsium, and these models, they just use positive examples, but there are other models that use the more traditional way is to use both positive and negative pairs with a general F divergence family. And then with an assumption on the joint feature distribution, they provide an optimal design for similarity function with Gaussian kernels, which shows the interesting connection between contrastive learning and kernel methods. And they characterize the properties of alignment and uniformity for F-mutual information and provide guidance in choosing proper F-divergences. And the objective of FMICL can be estimated with finite samples, and experimentally their framework is better than popular baseline by simply replacing the info and CE loss with the FMICL objectives. So if you consider a pair of random variables x and y with density p, the F-mutual information between x and y is this integral. But f here is a convex function, and px and py are the marginal distributions of this probability distribution. And this lambda in measure theory, we call it Lebesgue measure or dominating measure. There are common choices of f that can be found, and so this interesting paper, they derived a variational method by maximizing the dual problem, because in the dual problem we can have a lower bound, and then why not maximizing this one? So there are many different KL divergences, like KL or divergences like KL or Jensen or other divergences. Based on the F mutual interval, we propose a novel framework for contrastive learning. We characterize the properties of alignment and uniformity theoretically for general F divergences. And then we design the structure of function T, like this K of G of X and G of Y. This function G produces a d-dimensional normalized feature encoding on the hypersphere. And K is a similarity function that measures the similarity between two embeddings. And then we can write the objective of mutual information, as I said in previous slide, this one, because we have the lower bound, and then now we just maximizing this one. And if f is differentiable and the encoder function g is fixed, then this similarity function simply maximizes I as long as it is contained in the function class K. And we have one assumption that the joint feature distribution is proportional to radial basis function. But using this assumption, we can say with Gaussian kernels and the same setting, the optimal similarity function satisfies this relation that D here is the feature dimension and C is an absolute constant. So the algorithm, we have batch size of size n, for example 32, 64, and then weighting parameter alpha, we have constant mu and variance. So for each batch inside the epoch, for all k, we randomly sample two augmentations, and then we compute this mutual information. But we update this G here, we update them by taking a step to maximizing IF. If we choose the F divergence to be KL divergence, the objective that I showed you 9 here, this objective now becomes simply this supremum, which retrieves the objective of the alignment and uniformity. And if the batch size is n, for example 32, then with D, but D is the dimension of the feature space, if the real function is strictly convex, then all minimizers of second term satisfy this fact that the feature representations are distributed uniformly on the unit hypersphere. So it's a very big result that if we just satisfy that, then all samples are distributed uniformly. That is what we want. So by distributed uniformly, we mean that the feature vectors form a regular simplex, and the distances between all samples, as you see, the distances between all any pair you say are the same. and it reflects our intuition that the feature embeddings are evenly distributed. Although minimizing the negative term gives uniformity, the positive term is also needed for aligning similar pairs as we observe in our experience. Therefore, there is a trade-off between alignment and uniformity, these two important measures in contrastive learning, that shows if your contrastive learning algorithm is good or not, if it is collapsed to a single point or subspace or not. And suppose that the function t takes from a function class, then for any t, the estimation error is upper bounded with at least this probability.